We're given the following circuit where we seem to have two batteries parallel with each other and um, several resistors in parallel as well. And the question is asking that for the value of epsilon right here, if we want the current through the 7 ohm resistor to be 1.75 amps. And at first glance, it might seem like a basic algebra problem. This is a pretty basic introductory question for the Kirchhoff's laws. So we have the Kirchhoff's current law and Kirchhoff's voltage laws. And this is, if you're just beginning to use them, this question can be kind of intimidating. I know I got stuck on questions like this when I was just starting out learning Kirchhoff's laws. But we'll just walk through it step by step and just figure out how to apply them on this basic circuit. So when it comes to, we'll use the current law first. So the current law states that at a junction, when I split in two, the current through both branches will equal the original current. So in this case, we'll say that the current coming out of the 24 volt battery is equal to I. And when it gets to this junction right here, it splits off into, we already know that the current going this way is 1.75, and the current going this way, we can say will be I minus 1.75. Alternatively, I'll do it this way. We can say that the current going this way, and this is all very important to. It doesn't matter which way you set your current to be going. All that matters is you stay consistent with it once you start solving the problem. Sorry, I'm not sure what has on yours. Okay, we'll say that the current coming out of here is the I epsilon coming out this unknown battery, and they join together and they become I plus I epsilon equals 1.75. All right, so we have our equation for the current across that junction. All right, and then we'll move on to the Kirchhoff's voltage law, and that states that the sum of the voltages across any closed loop will equal 0. So essentially, if I pick any point on, let's say, the outside loop, if I pick this point right here and I go all the way around, the subtraction and addition of voltages will come out to 0, and that goes for any loop in the circuit. If I want to take this left loop, it will come out to 0 here. If I want to take the big loop, it will come out to 0 here. If I want to take this point right here, when I go around this loop, it will come out to 0 here. So that's just an important concept to keep in mind, conceptualize. So we'll go ahead and pick two loops. So a rule of thumb is when picking out how many loops you should write the equations for, you just need as many equations as you have unknowns. So in this case, we have two unknown currents. So we'll pick out two loops and write their voltage, the sum of their voltages. So in this case, I'll pick out the outside loop, and then I'll pick out this right loop. You could do it any way you want. You could pick out this left loop, and you could do the right loop. You can do, but I'll just go ahead and do that first, the outside loop. So we start with 24 volts, and we run into the 7 ohm resistor, which has 1.75. So we'll have V minus V across that resistor, which is the IR. So that'll be 1.75 times 7 minus the next voltage across the drop across the resistor, which is this 3 ohm resistor. And we know that the current going to this 3 ohm resistor is just I, because all the junctions meet back up here and they make I again, which is part of that current law I was telling you all about. So we'll have I times 3 equals 0. And you might be starting to see how just setting up these equations, these laws, can really help us in determining all those unknowns, because this is the only unknown in this formula. And once we figure this out, you can solve for I epsilon. But I'm going to write out both of the loops that we need anyway, because in the future, when you deal with more complicated circuits, it is crucial to have this skill down where you're writing all the loops you need out and everything. And we'll still use this second loops formula later to find epsilon. So I'm going to go ahead and write that. I said that the current is going this way, and we'll have epsilon minus, we'll have that 1.75 times 7 first, minus, and then we run into the 2 ohm resistor, which should have I, since it's a part of the same branch, we'll have I epsilon running through it. So we'll do that, equals 0. Okay, so from here, like I said, we can solve this equation, plug I in here, and then solve for this one, and then we'll just plug I in here, and we'll get our epsilon. And then I'm just gonna go ahead and do all that. So we'll have 24 minus, minus, let me calculate this real quick. 1.75 times 7 equals 12.25. So we'll have 11.75 minus I 0 times 3 equals 0. And from this we get that I is equal to 11.75 over 3, which is equal to, we'll say 3.917 amps. Okay, so now that we have this, that's pretty easy. Just gotta solve for I epsilon. So I epsilon will equal 1.75 minus I, which is equal to 1.75 minus 3.917, which is equal to, make this negative, add 1.75. We'll call that negative 2.17, I believe. Yep. Okay. Now you may be noticing that this current is negative, and that, when you think about it, when you realize that it actually means that the current is going this way. But it doesn't really matter which way the current is actually going, as long as you have set any direction, you just picked any direction at the beginning, and you stay consistent with it throughout the whole problem. You won't have any issues with that. We'll just use negative 2.17 amps for this problem. So you just plug everything into this equation now. We got epsilon, and I'll just move everything over to this side so it's easier. So we'll have epsilon equals 1.75 times 7 plus negative 2.17 times 2, and that will come out to 2. Let's say times 2, okay. 2.17 times 2 plus 1.75 times 7. And we'll get the answer of 7.91 volts. And that should be your answer right there.